Okay. Great. So we're going to learn about chapter 21.2, power lines and transformers. Yes, we are. So generally, power stations are not usually found in the middle of a city. They're, can be hundreds or more kilometers away from town, right? So, extremely high voltages are sent from these power stations through the power lines. Now, I'm sure you've seen those really tall towers with the wires hanging through.
Oh, yeah.
Right?
The one where my dad flew the helicopter and then it crashed and burned the thing.
Yeah. So, that's a bad thing, but exactly. So, we have these power lines that hold or transfer extremely high voltages. These lines reach local distribution centers where the power is sent to homes, businesses at much lower voltages. Transformers are used to reduce the voltage, commonly to 230 volts. So why do we need such high voltages? Why do the power stations send the electricity and everything at such high voltages?
To get the most to the people.
Okay, to get the most to the people.
So none of it gets lost.
None of it gets lost. Okay, we're on the same, on the same page.
Because if you send more at once, there's less chance of
Transformers.
Oh my god.
He did it. Yeah, I did it. Okay. So, power stations transmit electrical power around the country extremely high voltages, but why? The high voltages means that the current in the cables is relatively low. Because remember, if you remember back to when we calculated voltage, current, resistance, that sort of stuff, right? So you remember you had, let's just say a resistance, right, is constant. It's not going to change because you have the same kind of wire. So it has the same resistance through it. But if you increase the voltage now, that means that the current is going to decrease.
Oh yeah, I was right. Waste less energy.
So if you have these extremely high voltages, the current in the cable is relatively low, which wastes less energy. Now, why would it waste energy? If you had a really high current going through a cable, why would that waste energy? Any ideas?
Because, if you had a high current, why would it waste energy?
No. It's because of the resistance.
Oh yeah.
So if you have, if you think about it, if you have trying to shove a lot of something through the same amount of space, it's going to become difficult. And in this case, when you send a lot of current through something with the same resistance, it's going to get hot. It's going to warm up. And then you have a lot of heat. And that excess heat just gets,
And explodes.
No. The extra heat just, radiates from the wire. And that heat is energy that you're losing. So if you have a lower current, then you have less heat. So you're losing less energy through heat. Which is what we have here.
Danger of this.
So lower current means less heat. Less loss of energy. So as stated in the last slide, a transformer is used to reduce current. Okay? So we talked about this once already. We have two different kinds of transformers. Some increase the voltage, some decrease the voltage. So we use this transformer to increase voltage but decrease the current. So a transformer is a device used to increase or decrease voltage, usually up to 99.9% efficient, meaning there is little loss of energy. The reason for that is, from a power station to, say, your home, the electricity could go through upwards of 10, maybe even more transformers. Right? Transformers at the start to increase the voltage, transformers at the end to decrease the voltage. And if each one of those, say, lost 1% of the energy going into it, then after it goes through 10 of them, you're losing 10% of the energy that you started with. That is not very efficient. But the transformers they use are 99.9%, so you might lose 1% of the energy you started with from the power station to when it reaches your home. but I'm saying 10 transformers, that would add up to 1%. Right? So power stations typically produce 25,000 or 25 kilovolts, and then this is converted to about 400 kilovolts using transformers. And that's when it hits the power grid. Right? So the power grid is basically all those wires transferring all this electricity into towns, businesses, houses, whatever. So from the power station to the actual grid, we increase the voltage, and then from the grid to your actual home, you decrease the voltage again. All of that is to save energy. And it seems like a lot of work, but in the end, you're actually saving money, reducing costs, and that sort of.
People are willing to do anything
Yeah.
to
And
save
so
money.
you'll notice our man here getting struck by lightning. You'll see that around power stations or distribution centers or those high wires.
But why is it a guy?
I don't know, it could be a girl with short hair. You don't really know. It's a
The truth
silhouette
is
of a
unknown.
person. It's hard to tell.
One
Yeah.
man got hit by lightning 8 times and he survived.
Yeah, well, it
Then
happens.
he died by some.
So you were here for the conversation about what actually kills you. Voltage versus current. The current is what actually kills you. In fact, you can die from just 1 amp of current. Whereas, if you have 4,000 volts going through you, you might get burned, but you won't necessarily die if it's a very low current. So, yeah, we had that whole conversation.
That's a problem.
While you were gone.
Surviving.
Yeah, even like while you touch the electricity, you get shocked and you can't move and stuff.
So here is an example of a transformer. It's a better looking picture than the one I had last time. So this is our structure. There are 2 types of transformers, step up and step down. So what does a step up transformer do?
That
What's
puts
that?
up.
It has more
Increase.
spins on the secondary coil.
True.
Yes.
Step up
Yes.
will have more spins on the secondary coil.
And it increases the current thingy voltage.
It increases the voltage. So more turns on the secondary coil and increases the voltage. Step down is, well, the opposite. Less turns on the secondary coil reduces voltage. So here we have our primary coil, secondary coil. So depending on how many turns are here versus how many turns are here, you have a step up or step down. Okay? Very basic idea. It's not all that complicated. Now I'm not going to get into exactly how it works yet. That will be in the next section that I'll talk about. But there we go. So that's our basic structure, picture A. Now in B we have the circuit symbol for a
It
transformer.
looks like fat fingers, like someone with fat hands trying to grab something.
Trying to grab a ladyfinger, maybe? That's a chocolate
Oh,
dessert thing,
that is.
ladyfingers. So, it's 2 hands
When
going
you
for a
have
ladyfinger. No? Okay. So that is your circuit symbol for a transformer. Obviously, the left side there is the primary coil, the right side is your secondary coil. The middle is your core, usually iron. And for that, you don't have to put, 3 coils here, then 8 coils there, or something like that. Right? That's just how it will always look, whether it's step up or a step down transformer. Okay, so that's the basic circuit. Any questions about that so far? I talked about this last time, so it's really only new to you.
You heard it.
No. So as I said, there are 2 types of transformers. You have the, these guys, Decepticons, so just make sure you don't forget. Okay, 2 types. One's good, one's bad. Okay, that will be on your test. Yeah. Yes, the physics transformers are not bad.
2 of them.
Okay, so now we get into the math part of this.
Oh, damn.
So transformers always have an input and output voltage, right? So if it's a step-up transformer, you have an input voltage of, let's say, 10 volts, steps it up to, say, 20 volts, right? Step down, you have an input of, say, 50, steps it down to, say, 20, okay? So you always have an input and an output voltage. So depending on the number of coils, you can calculate different parts of this, right? So there are different parts of these coils, and
I'm taller than you though.
That's fine. That wasn't meant for you not to be able to reach it. It was meant for you to not go get it right away. Don't do it. I have it on tape that you're not doing what you should be doing. Okay. So, here's our formula. The voltage across the primary coil divided by the voltage across the secondary coil equals the number of turns in the primary coil divided by the number of turns in the secondary coil. So, short form, Vp over Vs equals Np over Ns. Okay? So, voltage primary, voltage secondary, number of turns primary, number of turns secondary.
This is gonna be on
IGCSEs?
the wiki thing, right?
Yes. Yes, it will.
Wait.
Because I need to like look it up more.
Well, I didn't go into this much depth with them last time.
What
I
does
just did a
that-
basic overview of the entire chapter, and then now I'm going into details of
What
the
does the
individual
N
parts.
stand for?
Number of turns in the coil. Okay? So, very simple formula. Nothing too complicated yet.
Yes.
So, let's try an example then. So, a transformer is needed to step down the 230 volt main supply to 6 volts. If the primary coil has 1,000 turns, how many turns must the secondary coil have? So, first thing I want you to do is draw a transformer symbol and mark on the information from the question. So, mark the input voltage. We don't know the output voltage yet. We know the input and output voltage, but we know the number of turns in the primary coil, but not the number of turns in the secondary coil. So I want you to draw
Our
a
turns,
picture, which will look like
if
this
they mean
here.
turns, does it mean I have to add more fingers?
No. Like I said, the number of turns, I don't want you to draw 1,000 little dots or little round things. That will take a while and a lot of space. So it's good to start with that just to see what you know.
I drew the fingers.
Okay, now fill in the information. So 230 volts for the primary input. So that's on the left side, primary. 6 volts on the secondary, which is on the right side. And then 1,000 turns on the primary coil, which is on the left side. So that's all I want you to do, is just mark that down. So it should look something like this. Okay?
What if I put the volts above the thing?
Doesn't matter. Your primary voltage is 230 volts. Your secondary voltage, 6 volts. And the number of turns is 1,000, but we don't know the number of turns on the secondary coil.
So primary is left, secondary right.
Primary left, secondary right. So now we just need to use our handy dandy formula here to figure out the number of turns in the secondary coil.
Okay, let's see.
So
VP.
write down our transformer equation, which is this, and substitute the values from the question into our equation. So we know VP and VS and NP, so we fill in those values,
Yeah, let's do it.
which will look something like
Wait, what are they on?
that. Well, then don't look at the board.
Okay.
So we have 230 volts for the primary voltage, 6 volts for secondary voltage, and 1,000 turns in the primary coil.
But they're equal then, so. Oh wait, do we have to do like the cross?
So now we need to rearrange and solve for NS.
How do we do that?
1,000 times
Algebra.
6 divided by 230.
1,000 times 6 divided by 230, what he said, equals number of coil or number of turns in your secondary coil.
Boom.
So
Don't count, but he has no
26
point.
point.
So 26.1 is the answer. But we obviously don't have 0.1 of a turn.
So it's 26.
So it's 26, yes. Round off to the nearest decimal. Because it will not be exact. Because remember, these transformers are 99.9% efficient. So there is always going to be some loss. Not a lot, but there will be a little. So your answers generally will have decimal points. So just round off to the nearest whole number, and that will be fine. Okay?
So it's 26.
Yeah.
So there are 26 turns in the secondary coil. Yes. That's the last one. Following along? Okay. Any questions about this example?
No, it's easy.
Yeah?
So far.
So far. So that ends this section. Okay? There is one more section, or two more sections after this. Why isn't that going?